So let's start talking about these transition metal coordination compounds. So we're going to need to review some stuff about transition metals and learn a little bit more about transition metals before we actually get into the coordination compounds. So of course, here's a periodic table. We've talked a lot about the main group elements. They're fairly easy to predict because their electronic structures are so predictable. The chemistry of the main group elements is pretty straightforward. However, the transition metals, so these guys here, and of course the intertransition metals, which are down here, they are much more complex. They don't have, again, these are all +1, right? Because they want to get rid of their electron and have a configuration like the nearest noble gas. Group 2, of course, lose 2 electrons again to look like they're noble gases. The non-metals are trying to gain electrons, so 1 for the halogens, and again, they're going to look like their nearest noble gas by gaining that single electron. But the transition metals, on the other hand, can have more than one possible charge state, and so that makes their chemistry a lot more difficult to predict. So again, just as a refresher, you're going to need to know how to write your electron configurations again. This is going to be important for predicting the properties of the transition metals, because a lot of their properties are going to be based on how many unpaired d electrons there are. Okay, so you're going to need to be able to write your proper electron configurations again. So again, the rules, well, no 2 electrons can have the same spin, right? This is the Pauli exclusion principle. This basically means that a single orbital can only ever have 2 electrons, 1 spin up and 1 spin down. Subshells are filled according to the following order. So again, we use the periodic table to actually follow this order. And I'll go over that again when we do some examples. Rearrange the configuration into the proper order. This is really important because the electrons fill this way, but they come off in this arrangement. And that's what we're worried about, is how they come off. Not how nature filled them to begin with, but how they're going to come off when they're being ionized. And then finally, electrons in degenerate orbitals. So in other words, we have the p subshell. The p subshell has 3 orbitals. We would fill those 3 orbitals singly, so with the same spin. So in other words, we'd put 1 electron in each order, all with the same spin, and then we will come back and start pairing them up. Okay, and this is called Hund's rule. And of course, the d subshell, which has 5 degenerate orbitals, so 5 identical orbitals, again, we would fill them singly, all with the same spin, and then we would begin to pair them up after we filled those orbitals. So for neutral atoms, the number of electrons is simply going to be equal to the atomic number, which of course is the number of protons, which is the whole number in the periodic table, right? The whole number above a particular element. So for example, neutral nickel has an atomic number of 28. And we are going to fill it like this. Again, I will demonstrate this tomorrow when we start going over problems. But again, just refresh yourself if you don't remember this from Chem 110. You need to go back and look how to write electron configurations, because you're going to need this all again. Okay. So basically, you're going to go across the periodic table where the group 1 and 2 represent your s electrons. Your other main group elements, 3 through 8, represent your p. And then your transition metals, as you recall, so that the 1s represent the period number, except for when you get to the d, the transition, it's n-1. So these are actually in period 4, but it's n-1. This is why it's the 3. And then there's the extra 8 electrons. So there's 8 d electrons. But again, this is the way they feel. We want to put it in what I consider proper order. So again, what we're going to do is we're going to put them in increasing principal quantum number. So that's the number here, right? So 1, 2, 3, and 4. Then within each a shell, so this red represents, all these represent a shell. There's a shell, there's a shell, there's a shell, and there's an unfilled shell over here. This is unfilled shell as well. So within a shell, we're going to put them in increasing order of energy of the subshells. So that's going to be S, P, D, F. Okay, so this is proper order. So this is the increasing energy of the electrons within a given atom. Now the orbital diagram then for the ground state iron atom and its ions. So again, we know that neutral iron has 26 electrons. So writing the shorthand form, and we'll talk mainly about how to write the shorthand form tomorrow, because that's really all we need. We're going to find iron on the periodic table. We'll go the whole way to the right until we get to the noble gas, and then up one, and that is going to be the core electrons. Then we'll go back to iron, go the whole way to the left across the periodic table, starting in that period. In this case, it's period 4. And then we're going to start filling. So remember, the 1 and 2, the group 1 and 2 represent the S electrons. So there would be 2 electrons there. Then we'd count in starting at the transition metals. And again, since this is period 4, N minus 1 is 3, 4 minus 1 is 3. And then we're going to count over till we get to iron. So we're going to count six elements before we get to iron. So that would be 3d6. Okay. So now this is the electron configuration for the ground state of iron. But of course, we got to put it in proper order. Okay, so we want the, well, it's already in proper order because we got the 3d6 and the 4s2. Okay, so again, according to Hund's rule, right, we're going to fill these things singly. We're going to fill these things singly, and then we'll come back and pair them up. So we can see then for a neutral iron, there is 1, 2, 3, 4 unpaired electrons. There's 4 unpaired electrons. So this is going to be important. You're going to have to write your electron configurations and then be able to draw a proper orbital diagram so that you can determine how many unpaired electrons are in the transition metal. Now for iron 2+, we have to go to the electron configuration that's in proper order, right? When we filled it, it was the 4s2 followed by the 3d6. But then we had to put it in proper order, okay? So that we ended up with, when we take off, so for iron 2+, we got to take off the highest energy electrons first. So that's the 4s2. So the orbital diagram for iron 3+ again shows that we have a total of 4 unpaired electrons. If you wouldn't have put this in proper order, you would have taken off this guy, okay, and one of these guys, so you're going to get the wrong number of unpaired electrons. And for iron 3+, again, we're going to remove the 2s and then 1 of the d, and so that looks like this. So iron 3+ actually has 5 unpaired electrons. Okay, so we'll again do some examples of that tomorrow. Okay, now there are anomalies within the building up principle, and these are things like, there's actually 21 of them, but these are the transition metal ones. So the chromium, copper, niobium, molybdenum, ruthenium, rhodium, palladium, silver, platinum, and gold. But again, on the exam, just use the regular building up principle. I do not expect you to memorize all of these. So just use the regular building up principle. But just to talk about these, so the expected configuration, for example, of chromium looks like 3d4 and 4s2, okay? But that looks like this. but nature likes symmetry. Nature really likes things to be symmetric. So the actual electron configuration looks like this, where we now have an unpaired electron in all of these orbitals. It's kind of like Hund's rule. And so we see this anomalous configuration for chromium. Okay, and as you go down, we also see it for molybdenum. Okay, so that's why this one's kind of odd. This is why it didn't follow up the building up principle, because it kind of liked, it's a little bit lower in energy to have this configuration compared to this one. Now that's not true for all atoms. So it's not a rule, okay? Copper, for example, looked like this. But nature, instead of putting the two paired electrons in the 4s, it actually puts and fills up the d orbitals. That's why copper generally has the most stable oxidation state of +1, because it basically just loses this electron, and then it has this pseudo-noble gas core. Okay, so nature likes to do that. So again, you see that for copper, and then below it is silver, and below that is gold. And so you see the same thing for those three elements again. Okay. Okay, so like the main group metals, transition metals are malleable, they're ductile, they're lustrous, they're good conductors of heat and electricity. They're metals, right? So they have the same properties as any of the other metals on the periodic table. Now, metallic bonding results from a sharing of valence electrons between atoms. So unlike covalent bonding, where the electrons are, a pair of electrons are restricted between two nuclei, or unlike ionic bonding, where there's a complete transfer of electrons from one atom to another, that isn't true for the metals. In the metals, the valence electrons are free to hop between any nuclei. So they're mobile. They're actually able to go from any atom to another atom. That's what makes them electrically conductive. So that's why covalent compounds are not conductive, because again, their electrons are fixed between two nuclei. Ionic compounds are not conductive because their electrons are fixed to a certain atom. Okay, so the metals, on the other hand, their valence electrons are able to be shared between any of the nuclei and able to move around. And that's what makes them electrically conductive. That's also what allows them to be good conductors of heat in a much more complicated way. Okay, so transition metals are harder and have higher melting points than the other main group metals, especially the 1A and 2As. The group 1A metals have melting points that are, some of them, just above room temperature. Okay, the 2As, again, not that hot, 100 to 200 degrees Celsius, and you'll melt them. But the Ds, the transition metals, on the other hand, because they have all these D electrons and the S electrons being shared between the different atoms, they have much stronger bonding. So the metallic bonding is much, much stronger in the transition metals than it is the group 1A and 2A. Okay, because they have those unpaired D electrons, which allow them to be shared. So metallic bond strength is roughly proportional to the number of unpaired electrons within the metal. Okay, so if we look at this, if we think about it, right, so just considering the D electrons. So there's the D electrons, and there's 5 D orbitals, and they're going to fill singly, right? So this would have 1 unpaired D electron, this would have 2, this would have 3, 4, and then 5. So magnesium would have 5 unpaired electrons. But then we start to pair them up again, right? So now one of the electrons are now getting paired up. So there's only 4 unpaired electrons in iron, 3 unpaired electrons in cobalt, 2 unpaired electrons in nickel, 1 unpaired electron in copper, and there's no unpaired D electrons in zinc, cadmium, or mercury. So with no unpaired electrons, you can see that the melting points of these metals are much, much lower. In fact, mercury is actually a liquid at room temperature. So again, much weaker bonding, okay? So now there is this weird little indent where you would expect to have the highest melting point. And again, those are for reasons that are well beyond this course, why we have this little dip here. But for the most part, the bond strength increases as the number of unpaired electrons increase, and then decreases, we have fewer and fewer unpaired d electrons. So again, like I said, zinc, cadmium, and mercury have the lowest melting point since they have all their d electrons are paired. Now, atomic radii. So we've talked about this before, right? So the atomic radii, even though the number of electrons are increasing as we go from left to right across the periodic table, so are the number of protons in the nucleus. And we talked about the effective nuclear charge in Chem 110. That's because only the filled shells shield the valence electrons. So the valence electrons don't shield one another because they're all sitting at approximately the same distance from the nuclei. But the core electrons are all sitting closer. And so that negative charge of the core electrons is canceling out basically some of the positive charge of the nucleus. But again, the valence electrons don't do that. So that's why we see this decrease in size. As the valence electrons see a more and more positive nucleus, well, they're attracted to the negative is attracted to the positive, and so they contract. They get smaller and smaller and smaller because the positive charge of the nucleus is increasing, so they get smaller. But then towards the end, there's just so many electrons that they start to repel one another. So this is the trend we see in size. They get smaller and smaller and smaller until the very end, they start to increase just because of basically overcrowding, okay? So again, we know that the effective nuclear charge increases. The effective nuclear charge is basically the charge that the valence electrons see or feel from the nucleus. Now, the second and third transition elements have nearly identical atomic radii, as you can see. 151, 144, 137, 138, 134, 136. Now, that's odd. You would have thought that they got bigger because there's a ton more of electrons. But again, it has to do with that effective nuclear charge. It just keeps getting bigger and bigger as you're adding more and more electrons. Okay. Next, let's talk about the density. So think about what density is. Density is mass over volume. So as the mass increases, you would expect the density to increase. But it's over the volume, right? So that would be based on the size. So notice at the end, remember we said they get bigger at the end again. So we see that same trend with size, but notice that it's actually inverted from the atomic size. It went from bigger atoms to littler, and then got bigger again. And now we're seeing just the opposite trend because the masses of these things are very similar, right? They're only increasing by a very small amount as we go across. So it's more affected by the volume, the change in volume, than it is the mass. So again, it is inversely proportional to the size because it's 1 over the volume. Okay. Any questions about that? Any questions about any of this yet? Okay, next, ionization energies. Again, we saw in Chem 110 that the ionization energies, for the most part, increase as you go from left to right across the periodic table. Again, that has to do a lot with the effective nuclear charge. The bigger positive charge the electrons feel or are attracted to, the harder it's going to be to rip those electrons off. So it's going to require more and more energy to rip off the electrons. And that's basically exactly what we see. There's a few anomalies where we see a little bit of a dip, but for the most part, the ionization energies increase as you move from left to right across the periodic table. And again, that is due to the increase in the effective nuclear charge as we move from left to right across the periodic table. Now, notice that we're looking at oxidation half reactions here, right? Because metals prefer oxidation. Metals prefer to give up their electrons to form cations. So this is just the opposite order that you see in the tables of standard reduction potentials. And that's because in metals, again, we know that oxidation is favored. When we have a positive potential, we know that that reaction is favored. It's spontaneous. So we can see that as we go across, so we're going from left to right, right? We're going from left to right across the periodic table. And you can see that as we move further, it gets harder and harder to lose those electrons. We've seen that with the ionization energies, right? So if it's harder and harder to lose those electrons, we expect the oxidation potential to drop as we move from left to right across the periodic table. And then again, we have this one oddity here, copper, which actually has a negative oxidation potential. So it really doesn't like to give up those two electrons. Okay. So again, we can see that all but copper are positive. And that is true for most metals. Most metals are positive, except for what we call precious metals. So things like platinum, gold, silver, they all have negative oxidation potentials. Okay. But most of the metals in the periodic table have positive oxidation potentials. They like to lose their electrons. So generally, again, we could write it like this. When a metal reacts with an acid, it generally gives up 2 electrons to form hydrogen gas. And again, it's positive, meaning that that's a spontaneous reaction. The ones with the positive, the negative oxidation potentials, they don't react with any normal acid. So most of the metals react with any acid to do this. However, for copper and the other precious metals, you have to use something with a higher oxidation potential. So you have to use nitric acid in the case of copper. Okay. So you can't just use HCl like we did here, for example. You have to use nitric acid. So nitric acid is much more nasty. It's a much better oxidizing agent than hydrochloric acid is. Okay, so nitric acid will dissolve copper, it'll dissolve gold, silver, platinum. So nitric acid is a much nastier acid than the hydrochloric acid. Okay, now let's talk about the oxidation states of transition metals. So we've already said that the transition metals, unlike the main group metals, have several stable oxidation states. So for example, here's manganese. So manganese in the +2 state looks like this light purple solution. In the +3 state, it actually forms a solid, this brownish manganese 3 hydroxide. In the +4 state, it'll form manganese 4 oxide, which is actually a completely insoluble oxide. Well, not completely, it's almost completely insoluble. So it forms this black solid material. Now, once we go to manganese +6, so this is this super permanganate, okay? It has a green color. Then here's permanganate. So this is the polyatomic ion that we know. And the manganese in this is in the +7 state. So you can see it's a very different color than this other manganese here, okay? So we can see here that I'm just listing this, there's more oxidation states of manganese, okay? So we can see that the transition metals have many, many stable oxidation states. So here's the most common. So we'll notice that scandium is +3, right? So that's where this 3B is coming from. The titanium is 4. Vanadium, its favorite is again +5. Now, chromium has a couple of very stable ones at +3 and +6. Manganese has +2, +4, and +7. Iron has 2 very common states of +2 and +3. Cobalt +2 and +3. Nickel's favorite state is +2. Copper likes +1 and +2. And zinc is always going to be +2. Okay? But there are other less common but easily obtained oxidation states. They're less common, but they're easily obtained. So you can see they're all over the board. So basically, again, we can see that this represents the maximum oxidation state, +3, +4, +5, +6, +7, until we get into the 8Bs, which are just weird. But and the 1 and 2Bs, again, they don't follow that because copper can be +1, +2, or +3. Now the zinc is +2. Now you could also have other oxidation states as well, but they aren't stable. I mean, you could force these metals into other oxidation states, but they're immediately going to react when they touch something else to go to one of these more stable oxidation states that we see here. So again, the highest oxidation state is for the group 3 through 7. We can see again, manganese has a +7. And again, the group 8 metals have a maximum oxidation state less than their group number. So again, these are the oddballs out. Same with 1B too, right? 1 has oxidation states not only of +1, but of +2 and +3, okay? Okay, so for the group 8 elements, again, the loss or sharing of all the valence electrons is energetically prohibitive because the effective nuclear charge is increasing, which means the ionization energy is increasing. So to remove all of these electrons requires a tremendous amount of energy. Like I said, you could do it. You could force these things into higher oxidation states, but they're immediately going to try to pick up electrons to go back to these lower oxidation states. Try some problems. So first we want to use the periodic table and write the electron configuration for the following ion. So basically, again, just as a quick review of how to write electron configurations. Basically, you're going to find that element on the periodic table. So that's osmium. So here's osmium. So we're going to write just shorthand forms because that's really all we care about are the valence electrons. So there's osmium. We'll go the whole way over to the noble gases up one. So it would have a noble gas core of xenon. Then we'll go back. So we're in period 6. So the group 1A and 2A represent the S subshell. So that's going to be 6S, and there's 2 of them. So that's 2. Then we would go to the transition metals. So now this is N-1. So this is going to be 5D. We'd put our 5D and would have 1 electron in there so far. But then for the lanthanide series, we drop down into the intertransition metals. This is N-2. Since we started at 6, N-2 is 4. And so these are the 4 Fs. So that would be 4F. And if you count across, there are 14 of them, representing the 7 4F orbitals, and the 2 electrons each would give us a total of 14 electrons in the 4F subshell. Now, once we filled that, we're going to come back up. Now, remember, we're back in the 5D again. So 5D, we already had 1, 2, 3, 4, 5, 6. So there's 6 5D electrons. So there's 6 5D electrons. Now, again, we're gonna ignore any of the anomalies that occur in the periodic table and their electron configurations. We're always going to use this idea of the building up principle to write these electron configurations. If you actually work with one of those anomalies and you need the electron configurations, you'll know it at that point in time. Okay, now once we've written the electron configuration, this isn't what we're interested in. We're interested in how the electrons come off. So we're going to rewrite this in the way in which the electrons come off. And so what we're going to do, we'll start with our noble gas core. We're going to put them in order of increasing energy. So we'll start with the principal quantum number. So that's the numbers 4, 5, and 6. So 4 is lower in energy than the 5 shell, which is lower in energy than the 6 shell. So we're going to go 4F14. Then our 5, so 5D6, and then our 6, so 6S2. So now that is the way the electrons actually come off these atoms. Okay, so now we have a +4, which means we're shy 4 electrons. So we got to remove 4 electrons. So we're going to remove 2 of these. So we're going to remove both of the S electrons. And then we're going to remove 2 more, right? That's 2, but we got to remove 2 more. So that's going to become a 4. And so the electron configuration then for the osmium 4 plus then is going to be xenon 4F14 5D4. Okay, so now when I look at this, now this is actually part of this second, I want to know, the reason we're doing this is we need to know how many unpaired electrons there are. So to do that, we need to write the orbital diagrams for these things. Now we're always going to ignore the core. And we could also ignore any filled shells, right? So that would have been 7 orbitals, 1, 2, 3, 4, 5, 6, 7. I don't care if you write circles, lines, or squares to represent your orbitals, but you do need to include all of them, whether they have electrons in them or not, and they do need to be labeled, okay? So, and then we have the 5D shell. So a D subshell has 5 orbitals. So 1, 2, 3, 4, 5. So that's our 5D. Now, the reason we don't need to worry about the pseudo-noble gas core is because they're always filled, right? According to Hund's rule, we're going to fill them singly with the same spin. So that would be 1, 2, 3, 4, 5, 6, 7. Now we can go back and pair them up. 8, 9, 10, 11, 12, 13, 14. So now we've accounted for all 14. So this is why we don't really worry about the noble gas core, because they'll all be filled. We don't care about the pseudo-noble gas core that says filled F and D orbitals, because again, we know that they're all going to be paired. What we're really worried about are the valence electrons. So in this case, these are my valence electrons, and this is what I'm most concerned about. This again just represents our pseudo-noble gas core. So I can see I have 4 electrons. So again, according to the building up principle, the Hund's rule, we're going to put them in singly with the same spin. So that's 1, 2, 3, 4. So we can see that the osmium 4 plus has 4 unpaired electrons. Okay. So how many unpaired electrons do the cobalt 3 and ruthenium 6 plus have? So give you a few seconds to write those electron configurations and then tell me how many unpaired electrons there are. So Hannah, how many unpaired electrons do you get for the cobalt 3 plus?
4.
4? Does anybody get anything different? Kaylee, how many unpaired electrons for the rhenium 6 plus?
I didn't get to do that one. I only got to do the first one.
Okay. Taylor, how about rhenium 6 plus?
Same, I didn't get to it yet.
Leah?
I'm trying to find it on the periodic table. Where is it?
Rhenium?
Yeah. Okay, so 1, 2, 3. Would it have 1?
You're saying 1?
Wait.
Hannah, how many do you think?
I'd also say 1.
1? Okay. Okay, so let's go through and do it real quick then. So starting
That
with
was just an educated guess, just saying.
the cobalt, again, you always got to start with the neutral configuration. So here's cobalt. We'll move over to the noble gases up 1, so it's argon. And then back to cobalt the whole way over, so it's period 4. So that's going to be our 4, and then again, these represent the S. So there's 2 of them. Then we get into our transition metals, which are the D, but it's N-1, so that's going to be 3D. And then cobalt is 1, 2, 3, 4, 5, 6, 7 over, so that's 3D7. But again, they have to be put in proper order. So that's going to be argon, 3D7, 4S2. Now, it's a +3, so the cobalt 3 plus, we're going to lose 3 electrons. We're going to lose both of the S electrons, and we're going to lose 1 of the D electrons. So that'll give us an electron configuration that looks like argon 3D6. So all we're worried about are the valence electrons. So this is a D subshell. So there's 5 orbitals in a D subshell. This is specifically the 3D. There's 6 electrons. We're going to fill them singly, according to Hund's rule. That's 5. We still got 1 left, so now we can come back and pair it up. And it doesn't matter which orbital you put them in, they're degenerate. That means they basically have the same energies, the same properties, except their orientation in space is different. Okay? So that shows us that we do have 1, 2, 3, 4 unpaired electrons. Now we'll do the same thing for the rhenium. So again, you always have to start with the neutral configuration. So rhenium go over up, so that's xenon. And then back to rhenium, back over, we're in period 6, so that's going to be the 6s2. Then we get into the transition metals, so that's N-1, so that's 5. These are the Ds, so 5D. And we're here, so we add 1. Then we jump down. Now that's N-2, so that's 6 minus 2. So that's our 4, and this, of course, is the F subshell. And again, you count them, there's 14 of them, so that's the 14 electrons. Then we jump back up. We're here now, so we're back to the 5D, right? N-1, so 5D. We only have 1, 2, 3, 4, 5. So that is 5. So there's a total of 5 5D electrons. Again, you have to put it in proper order to take electrons off. So that's going to be the xenon. So that's going to be the xenon, 4F14, 5D5, and 6S2. Again, this will be the valence electrons. So here were the valence electrons. These are now the valence electrons. And so that's what we're worried about. And so if we go to rhenium +6, well, we're going to remove 6 electrons. So that's 1, 2 from there. We still got to remove 4 more. So we're going to remove 4 of the 5D. And so that gives us xenon 4F14, 5d1. Again, we're only interested in the valence electrons. So there are 1, 2, 3, 4, 5 orbitals in the d subshell. Specifically, this is the 5d subshell. And we only have a single electron. You can put it in any one of those orbitals, and no matter how you put it, there's going to be one unpaired electron.
I have a question. I'm confused. Like, I get going through getting the gas, the S and the D, but I get lost like once you go to the Fs.
Okay, again,
Like
I
for the
strongly
OS
encourage you to do your homework because this is all Chem 110. Okay, so again, what you're doing is you're going to choose whatever atom it is, platinum. You go the whole way across, up 1. That is your noble gas core. Then you come the whole way back over. Now remember, the group 1 and 2 represent your S subshell with the 1 orbital and 2 electrons. The other main group elements over here, there's 6 of them. They represent the P subshells. So for example, these elements here represent the 4 P subshell. The transition metals, that's all the Bs. The transition metals represent the D subshell. And wherever you're at, it's going to be N-1. So this is 4, 5 minus 1 is 4. So this is the 4D subshell. Okay? Now, if we're getting into the these guys here, we'll never talk about these. These are very short-lived elements created in a lab. They're not of any use. Okay? But these are in nature. So up to 83, elements are stable. After the atomic number 83, so 84 beyond, they're all radioactive. They don't exist in nature. Okay? We create them in labs. So again, not really important to us. So again, if we're looking at one of these elements, well, first it's going to fill the 6s subshell. Then we go to the 5d, right? N-1 were 5ds. It'll put an electron in that first orbital. If you look at all the orbital diagram or all the electron configurations for these heavy guys, you'll notice that they always have one 5d electron in them. Okay, especially if you look at these. Okay, if you look at all of these, or these ones in particular, they'll have one 5d electron. That's the way nature does it. It puts a 5d electron in there first. Then it jumps down. So it jumps down. This is the lanthanide series, and that's this lanthanide series. These now represent the F subshell, and it's going to be N-2. So if we started here and went down, it was 6. So it's N-2. So these are 4s. So this is the 4, and these are the F. So this is the 4F subshell, which has 7 orbitals or 14 electrons. The 14 elements represent the 14 electrons. Then once we fill all of them, we come back up. We're now here. We already had one 5d electron, so this would make 2, 3, 4, and so on. Does that make sense?
Yeah, thanks.
Okay, make sure you do your homework. There are problems in here to refresh your memory on all of that. Okay, any other questions? Okay, again, this is important because most of the properties for transition metals depend on the number of unpaired electrons they have. Okay? Okay, so let's try another problem then. So this says, explain the general trends for the following properties from left to right across the first transition series, so scandium to zinc. So what happens to the atomic radius? Katrin, what happens to the atomic radius as I proceed from left to right across the periodic table?
It gets larger or smaller.
Say it again.
It gets larger,
Nope.
smaller.
So remember what's happening here. Yeah, we're adding electrons as we go across. So you would assume, So you would assume that they are getting bigger since we're simply adding electrons as we go across. But we have the nucleus. Okay, we have the nucleus and it has some charge. Then we have the core electrons. So this is some number which is different than n, some number of electrons, and those are our core electrons. Then on the outside sits our valence electrons. So these are our valence electrons. They all approximately within a given shell, okay, they approximately sit the same distance from the nucleus. But the negative charge of the core electrons cancel out the charge. So that charge normally we call Z, right? So that would be the atomic charge. However, these electrons don't see that full atomic charge because they're being shielded, okay, or this negative charge of the core electrons are canceling the positive charge of the nucleus. So we call that the effective nuclear charge. The effective nuclear charge is approximately equal to the nuclear charge minus the number of core electrons. So even though we're adding more electrons as we go across, we're adding them to this outside here. So what's happening is this keeps increasing. The number of core electrons remains the same the whole way across. So these electrons are seeing a greater and greater positive charge. That causes the whole atom to contract, to get smaller. Okay? So as we move from left to right, and we're always going to be talking about moving from left to right. First, they get smaller. But at end, begin to increase in size. So basically, it kind of does something like this. They get big, they get small, and then they get a little bit bigger again. Now, the reason they're getting a little bigger again at the end is because simply overcrowding. We start just putting too many electrons and they start to repulse one another. And so it just starts to get a little bit bigger at the end. Okay, so this would represent our scandium. This would be the whole way over to zinc. Okay, Hannah, what happens to the density?
The density starts smaller and then gets bigger and then goes down to small again.
So you're saying like this, it gets bigger and then smaller, right? Is that what you said?
Yeah.
Like this, right? So basically, yeah, it gets bigger and then it gets smaller. Can you tell me why?
It has to do with their radius.
Exactly, right? So density is equal to mass over volume. But the mass going from here to here isn't changing that much. Okay, so not changing that much. I mean, it is slightly increasing, right, as we go, but it is the volume, which has to do with the radius. So this follows, obviously, the inverse trend of atomic radius. So if they start out small, this number will be small. But as it gets bigger, this number becomes bigger, so so this becomes a smaller number overall. Then as we get to the end, they get small again. Okay. What about the ionization energy? Taylor, what about the ionization energy? What happens to the ionization energy?
Does it increase?
It generally just increases, right? And again, we'll see the same thing at the end, okay? But generally, they increase from left to right across the series. So basically, they simply increase. There are some small anomalies, increase from left to right. Okay. Why is that? Why do they increase? Why do they increase from left to right?
Because the electrons are more drawn to the nucleus.
I'm sorry, I can't hear you.
The electrons are more attracted to the nucleus.
And how I think you're right. Can you explain that a little bit more? Why are they more drawn to the nucleus?
Because the atomic radius is getting smaller.
Okay, I would agree. There's a second reason, more important than that.
Does it have something to do with how like the molecule, like the atoms will not repel each other as much, like they come closer?
No, the repulsion would actually make them go farther away. It would actually make the atom bigger and easier to ionize.
Okay. I don't know.
The effect of nuclear charge, right? The electrons keep seeing a bigger and bigger positive charge. It's harder and harder for them to escape that bigger and bigger positive charge. So yeah, the atoms are getting smaller. So those electrons getting closer to the nucleus make it harder for them to be pulled away. But on top of that, the effect of nuclear charge just keeps increasing. So that bigger and bigger positive charge makes it harder and harder to pull the electrons off. Okay. And then what about the standard oxidation potential? Now, these are oxidation potentials, not reduction potentials.
Was this like what we were talking about the other day with it was like a bunch of transition metals on a graph and you had the dots?
Well, that was talking about what the stable oxidation states were. That had nothing to do with the oxidation potentials.
Okay, then never mind.
Well, it has that. It's very similar to this. It's related to the ionization energies, right? The standard oxidation potential is basically how easily a metal loses its electrons. So what's going to lose the electrons easier, scandium or zinc? Which element loses the electrons more easily? Jada, what do you think?
I was gonna say zinc, but
Well, no, right? If the ionization energy increases, it gets harder and harder to remove electrons. The oxidation potential is how easy is it to remove. So the easiest is going to be scandium. The hardest would be zinc. So it is going to decrease from left to right. And again, basically for the same reasons that we've seen for the ionization energy. These two are very much related to one another. Okay, just in opposite ways. Okay, any questions on the trends? Okay, let's go to the next one then. Number 8 says, within the first row transition metal elements, titanium has a higher melting point, 1,668 degrees Celsius, and chromium has a melting point of 907 degrees Celsius. Why does chromium have the higher melting point? Why does chromium have the higher melting point?
Well, isn't it harder to break it apart because as it moves to the right, it gets the ionization energy increases, so it's harder to break it apart?
Well, do you remember when we talked in Chem 110 about the melting points of covalent and ionic compounds? What did their melting points depend on? The bond strength. The higher the bond strength, the higher the melting point. So that means chromium must have a higher bond strength than titanium. Why does chromium have a higher bond strength than titanium?
Is it because the electrons are closer together, so the strength is stronger?
Nope.
Oh.
Mentioned it earlier in the second problem that we did.
Is it about the pairing up?
Not pairing up,
The lone pairs? Unpaired? Sorry.
unpaired electrons, right? Titanium has how many unpaired electrons? There's titanium. How many unpaired electrons does it have? Taylor, what's the electron configuration for titanium? Shorthand form. What's the core?
Did you say Kayla or Taylor?
Taylor.
Taylor?
Yep.
Oh,
What's the
the-
core?
4s2.
Okay, but what's the core? The core electrons.
What do you mean? It would be argon. Oh, argon. And then 4s2, 3d2.
Right, so we went 2. Now the reality is, of course, that is argon 3d2, 4s2. So how many unpaired electrons?
Would it just be are there not any unpaired because the 2
How
and
many
2
orbitals in a D subshell?
2.
5.
Oh yeah, well yeah. So 5. But only
Those
2
3D.
were filled.
How do I fill them? There's
Put
2 of them.
a single arrow in one, then a single arrow in another one.
Okay, Hund's rule says we
Oh,
got to
so
fill them singly.
Yeah, there's
And
2.
then here's the, whoops, here's the 4s, and it has 2 electrons, 1 up, 1 down, so it's filled. So how many unpaired electrons does titanium have?
2.
2, right? So 2, 2. Then we look at chromium. So there's chromium. So Jada, what is the core, the noble gas core for chromium?
Chromium is going to be argon.
Okay. And then how does it feel?
It's going to be 4s2.
Okay.
4. 3d4.
1, 2, 3, 4. So 3d4. And then of course we got to put it in proper order. So how many unpaired electrons then?
There is 4 unpaired electrons.
Yeah, right. So our S is filled, and then we have 4. So 1, 2, 3, 4. So this guy has 4 unpaired electrons, and this guy only has 2. So this guy's going to have the chromium. The chromium is going to have the higher bond strength. So therefore, it's going to have the higher melting point. So just like we talked about in Chem 110, ionic compounds and molecular compounds, bond strengths, melting points and boiling points are dependent upon their bond strengths. So the more unpaired electrons, generally, the stronger the metallic bond. Okay, any questions about that?